So my talk will be about Frobenius homomorphisms in higher algebra, and the main goal of the talk will be to explain what that, or these, we will talk in fact about two Frobenius homomorphisms in higher algebra, so the main goal will be to explain what these are, how they relate to the ordinary Frobenius. But before I get into that main topic, let me start with two independent motivations. These will not be relevant for understanding the definition, but these are really why I care about these things. And the first one is something that I've worked on for the last couple of years. That's algebraic K-theory. I'm not going to tell you what algebraic K-theory is, nor what it's good for. So let me just say, this is a topic people have worked on for a long time. A lot of people, it has a lot of relations to many areas. The format of algebraic K-theory is that you have a ring, and then you assign to it the sequence of abelian groups, K star R. And these are the algebraic K-theory groups, and that's what we want to compute. And these have been introduced by Quillen 50 years ago. And the very first thing he did when he introduced these algebraic K-theory groups is he computed K-theory of the ring Z mod P. P is here prime. So throughout the talk, P will be a fixed prime. And then, of course, this is a field with P elements. And then he computes the algebraic K-theory groups of that ring. And, turns out that it's a copy of the integers in degree 0. And then it's completely concentrated in odd degrees, and there it's finite torsion groups. So I want to highlight the fact that in positive even degrees, these K groups vanish. And then the very natural next question after that is, the next natural ring to look at would be Z mod P to the K. And already that, turns out this is an open problem since then. People have tried doing that since then, and it's open. And a little was known, namely in a range of degrees. By Wickleik Angeldweit, he computed based on earlier work of Morton Brune and others. And this range of degrees grows with the prime. So for example, for the prime 2, it's really 2. And fortunately now with the methods I'm going to talk about in this talk, we can sort of compute those groups. And here's the result. So if I is very large, then we see this even vanishing pattern. Like in the case of Z mod P, we see that all the even groups are 0. And as a result, once you know that, one can compute what the groups in odd degree are, or at least what the order is. So these turn out to be all finite groups, and we can completely determine the order in that range. And in fact, actually we can do more. Not only do we compute it far out, but we actually set up an algorithm, or maybe one should better say a short chain complex which computes the K-theory groups. So let me say it in that way without going into the technicalities, that there is an algorithm which lets us compute all those groups. And in order to establish that this really works, let me give you a table. Of course, the precise content of that table is not super relevant. You're not supposed to read every line and remember it. But, let me first say, the first thing is here I'm displaying the 2-power torsion. So all these K groups turn out to be finite groups. And so the prime to P torsion is completely known. So the only thing that we had to do is to compute the 2-power torsion, and that's what displayed in this table here. For example, if we have something like 2 to the 4, 2 to the 4, that means the group is Z mod 2 to the 4 plus Z mod 2 to the 4. So there you have the tables. And I want to highlight two things. The first thing is, what was known previously are the things that are highlighted now, the first 2 rows. And I guess actually, in theory, in the literature, there was also a little bit about K3, but it turned out these results were slightly incorrect, so we had to correct them. And the second thing I want to highlight is this pattern of zeros. That's the even vanishing theorem. So here you see, as you go right in that table, you see that the sort of range where the zeros start to kick in gets lower and lower. And in fact, what we did is we first came up with this algorithm. Then we sort of feeded it into a computer, like Achim and Ben wrote a Sage program, and we computed it far out until the 40s. And then we immediately saw this pattern of zeros. And then it was clear there had to be something systematic going on. And then, after we knew that, we could prove that even vanishing theorem. Okay, and I will not say at this point too much about how this is done, in fact. But, the idea is to use something called trace methods, and that's kind of central to that Frobenius homomorphism. There the idea is that you want to compute this invariant K star, And you compute it by first computing another invariant called TC star, topological cyclic homology, and that in turn you compute by computing an even further invariant called topological Hochschild homology. And somehow how to climb that ladder from THH to K-theory, that's kind of the content of part of my talk today. Okay, so that's the first motivation, and here's the second one. So that lies at the very heart of what algebraic topology is. So when you teach a course about algebraic topology, you very often tell the people, the students, that, I mean, one of the goals is to define algebraic invariants to tell spaces apart. For example, I mean, I guess one of the very first applications is to prove that spheres of different dimensions can't be homotopy equivalent. And how do you do that? You just sort of write down the homology groups and you figure out they are different for these spheres, so they can't be homotopy equivalent. But then I guess like deeper in the course, you somehow try to distinguish spaces like CP2 and S2 wedge S4. And it's easy to see these spaces, in fact, have isomorphic homology groups. So homology is not good enough to tell them apart. But then, I mean, as probably most of you know, for those spaces, you can use the cup product. So CP2 has a non-trivial cup product, and S2 wedge S4 doesn't. So if you allow yourself to use the cohomology as opposed to homology and as a ring, then you can tell those two spaces apart. And now I can sort of keep escalating. Let's suspend these spaces. Right now, actually, on suspensions, all cup products are trivial. So there's no way I can use cup products to tell them apart. But now, fortunately, the fact that I had a non-trivial cup product on CP2, that implies that on its suspension, I have a non-trivial d-naught operation. And so I can use this d-naught operation to tell these two spaces apart. And now I guess I could keep going with that list. Then people have used messy products and all sorts of operations to tell spaces apart. And the question is, how long do we have to keep playing that game? And I claim the ultimate invariant from which all the previous invariants can be deduced is that instead of considering cohomology, you consider the cochain complex as a chain complex and equip it with a chain-level cup product. And that's kind of commutative and associative up to chain homotopy, so that's what we call an E-infinity ring structure. And all the operations above, like the cup product on cohomology, as well as the d-naught operations and the messy products, and all of that are consequences of that E-infinity structure. And why do I say this is the ultimate invariant? So that's a very beautiful theorem of Mike Mandel. Namely, he proves the following: if you have two spaces, say of finite type, simply connected, such that the associated cochain algebras are equivalent, then the spaces already were homotopy equivalent. So that tells us, I mean, we can't do better than that. We can completely distinguish at least simply connected spaces by this invariant. And I think this is, I mean, one of my favorite theorems in math. And I mean, this is actually an integral version of Sullivan's rational homotopy theory. And I guess actually, once you see that, you can ask yourself, well, can we do better than that? Can we say, well, for example, do all E-infinity rings arise from this construction? And I mean, it's very easy to see that the answer has to be no. But also you can ask, can I also understand maps? Like say, I want to understand mapping spaces between two given topological spaces. Can I understand that in terms of the mapping space between E-infinity algebras? And in fact, Mandel's computation shows us this can't quite be true. So what you have to do is, I mean, he computes these mapping spaces for us, and you see it's off by a factor of S1. You somehow see immediately that you have to take some extra structure into account onto the cochains of a space. And once you sort of allow yourself that, then the answer is yes, actually, and that's kind of part of using this Frobenius homomorphism I'm going to talk about, a very beautiful theorem of Alan Yuan, a recent one. He proved that if you equip these cochains, and I guess you work over the sphere, as I will detail in a second, you equip it with a trivialization of this Frobenius, then it turns out that you get an equivalence of categories. Okay, so that was my motivation, and now I want to talk about the Frobenius homomorphism in higher algebra. So let me first tell you what I mean by higher algebra. So higher is meant in the sense of higher category theory. And I guess this area has also, I mean, it's going by very different names, like sort of, I guess Waldhausen termed it brave new algebra. And the idea is always the same. The idea is to sort of take concepts from ordinary algebra or ordinary category theory, like you would replace the concept of a set, you would replace it by the natural homotopy theoretic or higher categorical analog, which is the space. And then an abelian group in that setup would be replaced by a spectrum. So a spectrum I think of as a generalization of an abelian group. And let me mention, I guess the other days we've seen a lot of homological or derived geometry. There you would maybe replace an abelian group by a chain complex. And that's maybe a slightly different flavor of higher algebra. I want to use spectra specifically because the rest of my talk would not work if I did chain complexes here. Like for different applications, chain complexes might be the right choice here. But as I say, that's why I say higher algebra, to specifically mean like with spectra. And then the integers, which is the initial ring in ordinary land, that gets replaced by the sphere spectrum. And I guess for those of you who don't know what the sphere spectrum is, the way I think about the sphere is somehow while the integers are just a discrete collection of points, the sphere is somehow consisting of like wobbly points. Every point has this fluffy nilpotent neighborhood or a lot of self-like symmetries, self-maps. That's kind of how I drew the sphere right here in infinity land. Okay, and then, I mean, the concept of an associative ring gets replaced by an associative or E1 ring spectrum, and the concept of a commutative ring gets replaced by a commutative or E-infinity ring spectrum. And one thing that is very important is there is actually ways to transition between the two lands. So what you can do is you can start with a thing in ordinary land like a set and consider it as a space with a discrete topology. Or you can take a abelian group and consider it as a spectrum, the associated Eilenberg-MacLane spectrum. And the same for rings, they give rise to a ring spectrum, and that's actually a fully faithful functor. So somehow ordinary land embeds fully faithfully into infinity land, and there's also ways back. You can take homotopy groups. If you have a ring spectrum, then its homotopy groups will be an ordinary commutative ring. And these are the ways how to transition between the different lands. Okay, and of course, I mean, the right-hand side is at the very heart of homotopy theory. So we study ring spectra and spectra. I mean, I guess Whitehausen was interested to compute different morphism groups. There's a lot of, I mean, this is the content of stable homotopy theory. And this kind of the point of this dictionary is to use methods we learned and used in ordinary algebra and translate them into this higher world and sort of take advantage of like concepts there, like deformation theory, the cotangent complex and stuff like that. And that is kind of the spiel that I want to propose here, and sort of we want to do that to the Frobenius homomorphism. Well, are there questions, first of all? If that is not the case, then I'm going to tell you, was there a question? I mean, the right-hand cat is grinning. Okay, good. So let's talk about the Frobenius homomorphism. What is the Frobenius homomorphism? If I give you a commutative ring, then there's this homomorphism sending an element in the ring R to its p's power. And as we all know, if we consider this as an element in R mod p, then magically it happens that this is additive. And that's the Frobenius homomorphism. This is very important to study FP algebras in many respects. And in fact, a little less well known is actually that there's also an associative version of that. That has sort of been used in conjunction, for example, with the Kaplansky conjecture. And I guess initially you might wonder, how can this even work? Because, I mean, obviously if you want to make this freshman dream work, you need the binomial theorem for the Frobenius to be additive. So there's no way in associative rings this can work. But of course, as mathematicians, we just make the world as we like it. We just quotient by the thing that obstructs the Frobenius to be a homomorphism. So we just quotient by the subgroup generated by commutators. And here I really mean the subgroup generated by commutators, not the ideal. So these quotients here are not rings. But these are just abelian groups, and then it's, I mean, very easy with virtually the same proof to see that this is actually a homomorphism of abelian groups. So that's the associative Frobenius, and these are the two versions, the two incarnations of the Frobenius that I will generalize to higher land. So the first version, the format of the first thing I'm going to explain is if you have a commutative ring spectrum R, then there's a Frobenius homomorphism from R to the higher world analog of the mod P reduction, and sort of I will argue that this is the Tate construction that's displayed here. So I'll tell you in a second what this Tate construction is, but for now, let me just say this is the higher world analog of the mod P reduction. And then there's also the associative Frobenius. That's a homomorphism on something called THH, which I will also introduce to THH Tate CP. So THH, I want to think of the higher world analog of quotienting R by these commutators. Okay, so that's the format of what I'm going to explain now. And yeah, let's first start with the Tate construction. G is a finite group, and for us, G will actually always be the group with P elements for P prime, so the cyclic group CP of order P, and it acts on an abelian group. Then there's a well-known map called the norm or the trace, which just sends an element in the co-invariance of the G action on M to the invariance by just like translating of, by summation over all translates of that element. And that's a group homomorphism, and sort of the kind of thing I want to consider here is the co-kernel of that map from the norm map, from the co-invariance to the invariance, and I will write this as M upper G modulo norms. So I think of somehow the image of the co-invariance in the invariance as norms, and then I sort of quotient by those. That's the kind of object I want to consider, and why do I want to consider that? So if G is a group CP with P elements, and I let it act trivially on a group M, what is the Tate construction? Well, I guess the action is trivial, so the invariants agree with M, and the co-invariants also agree with M, but the norm map is given by multiplication with P. So the co-kernel is just a mod P reduction. And this is admittedly a very complicated way of introducing the mod P reduction of an abelian group, but that's the kind of thing we do in higher land. So yeah, this is kind of part of the spiel. Sometimes you have to say things in ordinary land in a somewhat convoluted, complex way in order to sort of carry it over in the right way into higher land. So the norm here is a map in homotopy theory. Actually, G is a spectrum with an action of G. G is actually still an ordinary finite group. Again, most of the time it will be CP, but X is a spectrum, Gx on X. And then I have a higher analog of this norm map, which now goes from the higher categorical version of the co-invariants, which are the homotopy orbits, to the homotopy fixed points. So that's, and actually I should say, both of these norms are an instance of a very general construction. You cannot only do that for spectra, but for chain complexes. In fact, for every stable infinity category, you have such a norm. I guess the category has to have the appropriate co-limits and limits, but then you have this norm, and actually even for additive infinity categories. Okay, anyways, I'm not going to explain how to construct that. Just trust me that this can be done. And then the definition of the Tate spectrum is that you just take the Tate construction to be the cofiber of this norm map. For any G action on any spectrum, we define this thing called X Tate G, and that's called the Tate spectrum. And sort of what I want to advocate is what we're going to do most of the time in this talk is we're going to consider X to be a spectrum equipped with a trivial action of the group CP, and then we consider the Tate CP construction. And that is our higher analog of the mod P reduction. At least in applications, this will play this role. And there's this amazing result that if you now do that, so if you take this series and consider the Tate construction to be the higher analog of the mod P reduction, then this huge miracle happens to the theorem of Lin and Gunnar-Vardena that if X actually happens to be a finite spectrum, by finite spectrum I mean like built out of finitely many copies of the sphere, like finite cell complex in spectra, then actually this Tate construction is just the P completion. And I know it's hard to appreciate that if you haven't seen that before, but this is like a real miracle that somehow the mod P reduction in ordinary land corresponds to the P completion in higher land. And that's actually at the very heart of why these higher categorical methods play such an important role. Because very often if you in ordinary land in algebra have to restrict to a characteristic P to do something, then you all of a sudden can do it in mixed characteristic. That's kind of part of why these methods are so powerful. Anyways, this is an amazing theorem. I still don't understand why this has to be any right to be true, but it can be proven. Okay, and right, so now we have understood the arena. We understand what the Tate construction is, and sort of I told you that the Frobenius is going to be a map from R to R Tate CP. Now let's get into the construction of the actual Frobenius. So let's do the ordinary world analog first. So the Tate diagonal. So here's the thing, like take A in a abelian group, and then we consider the diagonal map. We just do P tensor copies of A itself, and we send A to this diagonal element. No problem, that's a well-defined map, except, well, it's not additive. Obviously, if I input A plus B, then, I'm going to expand out, you get all these annoying mixed terms. But the thing is, as before, we can just make it additive, because you just observe that all these annoying mixed terms, all these terms are norms. So as a result, if I quotient by the norms, this is exactly what makes this map additive, right? So I guess, it's a little bit of an exercise, but it's not really hard to see that this becomes a group homomorphism. So that's a kind of diagonal of an abelian group, or that's what I want to advocate as being the diagonal of an abelian group. And if you're on this exercise, maybe you want to do the second exercise as well, that if A is actually an FP torsion, an FP vector space, so a P torsion group, then this map is actually an isomorphism. So this is a little harder exercise. So it's keeping escalating, but it's still doable. Okay, good. So That is what we know in ordinary land, and here's a higher world analog. So the claim is that whenever I give you a spectrum, there's a natural transformation from that spectrum to the p-fold tensor power. Now we tensor over the sphere, and then raise it to the Tate CP. And maybe I should have said this before, like the group CP is the X by cyclic permutations, of course, on the tensor factors. Maybe I didn't say that before. Okay, so this is actually such a map, and I guess one way to prove this is to observe that the right-hand side as a functor is actually exact, and then this is obtained by a sort of categorification of the proof that the left-hand map was a group homomorphism, and then by some fact that the identity is initial, as I have proven in a preprint, you can see that there's a unique such map. And ignore the lag symmetric monoidal. This is just to make the map unique. Otherwise, there is just a map. Okay, so there's an analog of this map. I want to think of it as a diagonal. And the amazing thing is that actually, again, if X is p-complete and bounded below, then this map ends up being an equivalence. So this is actually, in the case X is a finite spectrum, this follows from the theorem of Lin and Gunnar-Vardena. For X finite type, it's the theorem of Rocknes and Nielsen, and for general bounded below X, I proved this with Peter Scholze. So again, this is the second example of where mod P reduction gets replaced by P completeness in higher land. Okay, and just now we've only restricted to the group CP. Let me just say one thing that I conjecture to be true is if G is a general group, or actually G is a finite P group, but there's a more general conjecture for general groups. It's just a little harder to state. If G is a finite P group and X again is a bounded below spectrum, then the diagonal map going to G tensor factors of X, this is an equivalence. And I should say, there's this little phi coming up here. That's an analog of the Tate construction, which I will not introduce here. This is what I call the proper Tate construction. And this is closely related to the so-called Hill-Hopkins-Revell norm being Borel complete. And this theorem, again, is true if X is a finite spectrum by means of the Segal conjecture, as proven by Gunnar Carlsen. And so John Rocknes and Bergsacker recently told me, recently meaning last week, that they now think they can prove this, and they're in the process of writing this up if X is finite type. But I conjecture this to be true even more generally. Okay, so anyways, so the thing we want to take away is that there is this Tate diagonal. All the rest are just computational results about it. Once you have the Tate diagonal, now we can look at the Frobenius, and let's again play that spiel and say what the Frobenius is in a as complicated as possible way. So we have an ordinary ring. Let's look at the diagonal we had before, just sending R to P tensor copies of R. And then the multiplication of that ring is a map from, I multiply P tensor factors together and go down to R. This is an equivariant map when I put the permutation action on the source and the trivial action on the target. So in fact, as a result, I get an induced map on this quotient, but the target is then R mod P. And that is just a complicated way of writing the Frobenius homomorphism of a ring. Okay, and this is exactly the kind of thing we generalize to higher land. So R and E infinity ring spectrum, then we just define the Tate-valued Frobenius to be the composite where we do this Tate diagonal, delta P, and then we compose with the multiplication to the Tate CP. Again, for an E infinity ring spectrum, this is an equivariant map, and everything works out. That's the definition. And well, I guess now, at this point, I guess I'm obliged to tell you that this is a non-trivial map and all of that. Let me just give you one example. There's a lot of examples I could give here, but let me give you just one, which I find personally very interesting. If you just input cochains on a topological space M, and say cochains as well as an F2, then you have the map phi 2. And let's look at the effect on homotopy groups. So the homotopy groups of the cochains are the cohomology groups of M. And it turns out that the homotopy groups of the Tate construction, these are just the Laurent power series ring over the cohomology of M. It's a little computation in Tate cohomology. And then the claim is this map is actually sending an element X to the sum over all its Steenrod powers, SQIX, T to the minus I. So in fact, this map reproduces for you all Steenrod operations. And I would actually even advocate using that as a definition of Steenrod operations. And so there was very recent papers on that by, I think, one by Lawson and Glassman and one by Dylan Wilson, where they use this as a definition and develop all the properties of the Steenrod algebra, like the Adam relations from that. And it's very beautiful and slick. So in fact, actually more generally, I could say that, I mean, the Tate-valued Frobenius always has to do with power operations. And I mean, every ring spectrum, for example, for Ku, we can reproduce Adams operations. And I guess I could also do that for odd primes and so on and so forth. So yeah, I think this is a very interesting map, and it's kind of a miracle that you just, the analog of Frobenius reproduces all that stuff for you. Okay, so that's what I wanted to say about the Tate-valued Frobenius. And now let me get back on one slide to my initial motivation about spaces. So what we can do is actually one thing by the Segal conjecture thingy. If R is a finite spectrum and P-complete, then we've seen before that the Tate construction is equivalent to R. That is kind of the Segal conjecture. As a result, I can interpret this Frobenius as an endomorphism of my ring spectrum. Then it maybe starts looking more like the Frobenius you're used to from ordinary land. And so I can study that in this case. And for example, if M is a finite space, that was the setting we were after, we can look at the cochains as well as in the sphere, aka the Spanier-Whitehead dual of the space. And I mean, say as well as in the P-complete sphere to make everything P-complete. And then it turns out, actually, you can study this Frobenius, and it turns out it's equivalent to the identity map. And I mean, this is, I mean, yeah, it's a little bit of a computation. I mean, there's this kind of magic trick where you say it's true if M is a point by inspection, and then there's this kind of thing that every space is a co-limit of points, so it follows from that, in fact. Anyway, so this is like black magic, but it works and tells you that the Frobenius on every cochains is the identity. And so this is actually a property, a distinct property that cochains on a space have, that the Frobenius is the identity. And this is actually what Yuan proves. If you start with a finite simply connected space and you do that, you get an E-infinity algebra over the sphere. And then for every prime, it turns out that the Frobenius is homotopy equivalent to the identity. So let's take that as an input datum. That's the kind of extra structure I want to put on the cochains. And once you do that and you have a homological condition, I mean, this corresponds to simply connected on the left-hand side, then somehow you see that this is an equivalence of infinity categories. And I should actually say I highlighted this word coherent because I'm lying here. So and the way I'm lying is the following. So I'm not just saying that the Frobenius is equivalent to the identity, but I'm saying that in a coherent way. So somehow you also have to say something for the composite of the Frobenius with itself. I mean, once you think about it, you have two ways of identifying the composite of the Frobenius with itself with the identity if you have a trivialization and you want to sort of fix a homotopy between these two ways. Anyway, so I mean, and this is actually in fact what Yuan has to do. I sort of thought this theorem was true before I had realized the subtlety. And then sort of fortunately Yuan realized this subtlety and sort of worked it out. Anyways, it's a beautiful theorem, and actually here I conjecture that there's a more general version is true, because you know, like if you take homology, this is usually a good operation for finite spaces, but for infinite spaces it destroys stuff because it dualizes. We don't want to dualize. So in fact, I claim that conjecture something like this is true if you just say simply connected spaces and you work with chains as opposed to cochains. And I mean, aka the suspension spectrum, I mean, this is actually now not anymore an E-infinity algebra, but it's an E-infinity co-algebra, right? The cross product on cochains, on chains will give you like a co-algebra structure. And then, I mean, the first part of this conjecture is that you can make sense of the Frobenius on co-algebras as well. And I can do that. I detailed that, for example, in my proceedings. And moreover, you need to make it coherent. And making it coherent, actually, this action, this Frobenius, relies on the conjecture I had on the last slide. So once we can sort of settle the conjecture on the last slide, we can make it coherent, and then I sort of this conjecture, both sides in this conjecture make sense, and I conjecture it to be an equivalence. Okay, good. So that's as much as I wanted to say about spaces. Are there questions? Otherwise, I proceed to the Frobenius on topological Hochschild homology. So let's do that. So where are we? This is the old slide. I bring it up again. So that's what we wanted to do. We wanted to define the right-hand column. Now we've done the upper one. And now we want to proceed to the lower one, the Frobenius on topological Hochschild homology. So that's a map from, I mean, as I said, it was a generalization of this associative Frobenius thingy on these quotients. So let's first talk about topological Hochschild homology. And since it's supposed to be a higher analog of these quotients, I mean, let's just look at this quotient. I mean, let's write this in a very complicated way, as usual. So what we can do is, I mean, if R is a ring, it's also a bimodule over itself, right? By left and right multiplication. So it's an R tensor R op module. And I can also like switch the orders of the two factors and act on it. Then it's also a right module of over R tensor R op. And now I take it as a left module and a right module and tensor the two together over R tensor R op. And it turns out that this actually gives you this quotient. Okay, that's what happens, and I mean that's what we do in higher land. So we just define topological Hochschild homology to be this tensor product in higher land. And of course, I guess, this is not specific to topological Hochschild homology. This is typically also done for Hochschild homology, which many of you have maybe seen. You do the exact same thing, just in chain complexes, as opposed to spectra, and then it's just called Hochschild homology. And so the T just stands for doing it in spectra, for topological. Okay, so that's the definition of topological Hochschild homology, and here are a bunch of facts about it. If R is a commutative ring spectrum, then THH of R as well is a commutative ring spectrum. And as a result, the homotopy groups of THH form a graded commutative ring. So that's very often useful. Even though this is the analog of the associative Frobenius, we will actually exclusively apply it to commutative rings. But somehow, in higher land, even the analog of the associative Frobenius and the commutative one differ. Second fact is there's an S1 action on THH. This is less trivial. So this relies on an insight of Kohn, who in the analog setting for Hochschild homology constructed something which we call the Kohn operator. And if you transfer this correctly to the world of spectra, you see that this gives you an S1 action on the spectrum THHR. That's what Böckstedt had done. Okay, and so on the computational side, there's one and only one fundamental result in the area. And that's what we do is we take the ring FP. That's an ordinary land ring. We consider it as a ring spectrum, and then we compute its THH. So the homotopy groups are a graded commutative ring, and the result is that this is just a polynomial ring on a single generator in degree 2. And I want you to appreciate the simplicity of that result. We're tensoring stuff over the sphere. So usually if you do that, all hell breaks loose. Things get really complicated, but this somehow magically simplifies to such an easy and beautiful formula. And in the last years, there has been a lot of work in the area of THH and a lot of progress. And I claim that every single piece of progress relies on this calculation. All these perfectoid methods and work of Butt, Morrow, Scholze, and others relies on this single calculation. And funnily enough, actually, one can, for example, use this and deduce Bott periodicity in complex K-theory from it. So, that's something I worked out with Lars Hesselholt in our in a write-up, and also I think Kaledin has. So this actually somehow we call it Böckstedt periodicity, and somehow it's in some sense more fundamental than Bott periodicity because it implies the latter. But I'm not saying this is a good proof. It's super complicated. It uses a lot of other stuff, but at least it works. Okay, good. So what's the Frobenius on THH? So now I claim that once you understand what THH is, you can write down a map phi p called the Frobenius that has in slightly different form first been done by Böckstedt, Chiang, Metzen in their initial work. Not quite in this form, but it also follows from their work. And I guess we give a new way of thinking about this map, and I will not give you the exact definition, but I'm just telling you it's constructed from the Tate diagonal again. And the mere reason I'm not going into that is because, THH had these several tensor factors of R. Basically what you do is you expand out what this tensor product means and apply the Tate diagonal to everything. You get tons of factors floating around, and then it's an exercise in combinatorics and concentration to see that you can use that to get a map into THHR. The upshot is just that it again uses the Tate diagonal. Okay, so that's the Frobenius on THH, and it turns out it plays well with this Kohn style S1 action. And it's also related to the commutative Frobenius I alluded to a couple minutes ago. Namely, if R is a commutative ring spectrum, then we have both, right? So we have the Frobenius on THH and the Tate-valued Frobenius. And if we do the ordinary world analog, this would just be the same, because then R mod commutators is R, and the maps are the same. And the higher statement of that sort is that we have a commutative diagram like this. So in fact, the Tate-valued, the THH Frobenius factors the E-infinity Frobenius in such a way. So part of the statement is that then the maps exist. Okay, so that's the relation between the two Frobenius operators. And let me also say that I will not go into that, but one can start calculating with this Frobenius. For example, in the example of Böckstedt's calculation of THHFP, one can completely calculate this Frobenius. And what happens is you see it's an isomorphism in non-negative degrees. So that's a very important pattern. In fact, you see that actually very often it's an isomorphism in non-negative degrees. For example, by a lot of theorems, by a lot of people, this is true for the following ring spectra, like the sphere. Then it reduces to Segal conjecture, the integers, by, I guess, calculations of Bergstedt-Madsen and other people. And like for MU, BP by Rocknes-Nielsen's results. And in fact, by very recent results of Butt and Matthew, this holds very true for like what they call Cartier smooth rings. So in a very huge class of rings, it's true that this Frobenius is actually an equivalence, at least in high enough degrees. So this is closely related to the Quillen-Lichtenbaum conjecture, like, if you know what that means. Okay, so that's what I wanted to say about the Frobenius on THH. Now let's get back to our first motivation, so to close the bracket and see how we use this now to compute K-theory. So remember, we wanted to climb that ladder in the case of Z mod P to the K. We want to start with topological Hochschild homology and compute K-theory. So now we have to understand how to climb up here. So the first thing is there's an intermediate layer in the game, which we haven't talked about, topological cyclic homology. So topological cyclic homology was defined by Bergstedt, Chiang, Madsen, and I'm not going to say anything about how they defined it. Sorry, Eep. But sort of the key point is that it receives a map from K-theory, KR to TC, and this map is actually often, I mean, it's called the cyclotomic trace, and it's often actually an isomorphism. So somehow the upshot we want to take, I mean, I'm not going to, I mean, there's a lot of theorems along these lines when it is an isomorphism, most notably a deep theorem by Dundas, Good, William McCarthy. In a recent, like in the commutative world, this has been recently improved by Clausen, Matthew, Morrow. At least in the case we care about, Z mod P to the K, this map is just an iso, at least if we restrict to the P power torsion. I mean, I'm writing P completeness here, but all are finite groups. So we know the P power torsion can be computed through computing TC. And so now the question is, how do we get at TC, right? And so actually this tells us roughly that we can climb the upper ladder. We can go from TC to K-theory. And now how do we get from THH to TC? And my claim is that once you understand THH with its S1 action and the Frobenius operators, then you can get TC. So it merely depends on those guys. So that's the result. And maybe, you know, let me say the correct result, because I feel a little bad about having such a sort of zoomed out result. Here's a precise statement. So you define an infinity category of like cyclotomic spectra, where you just look at spectra equipped with an S1 action and operators phi p. And nothing else, just the operators phi p, one at a prime. No interprime relations, nothing else. It's kind of a, and for the experts in the room, the S1 action is as naive as it gets. Like naive S1 action, not a genuine homotopy theory S1 action. And then you just, I mean, consider this category, and THH is an object in that category, and then TC is just the mapping spectrum from the unit to that. And I think somehow the vision that this should be true is very old. It's due to Hesselholt, and I guess also Blumberg-Mandel had a version of that. I think Kaledin once gave an ICM address where he conjectured something like that to be true, but this was always with a more complicated category of cyclotomic spectra. Part of this is here that this category of cyclotomic spectra really only depends on the Frobenius homomorphisms and THH. So the name of the game is understand THH, understand it with its Frobenius operators well enough so that you can calculate TC, and then TC is basically K-theory. That's kind of the name of the game that we keep playing. And that's exactly what we do to compute K-theory of Z mod P to the K. And somehow I think there's been a lot of progress in the recent years on this subject, and I feel actually we're only at the beginning of it. So at the moment, like all these like long-standing results in K-theory keep falling exactly because this strategy now can be implemented very effectively. So as I say, like I think we're just like looking, I mean, we just basically took Z mod P to the K because it was clear that this was desirable to do, but somehow I think that's not the end of the methods at all. Okay, anyways, let me be a little bit more honest and give you some details. Because of course, I mean, you need some additional ideas to do it actually. So let me just, on my very last slide, give you some of those ideas. So if you actually want to calculate TC of Z mod P to the K, as I said, you want to understand THH, you want to understand it with Frobenius actions, and you want to take advantage of that. And the idea is actually that we stole from, I guess, what people did in P-adic-Hodge theory is kind of to work relative to a uniformizer, relative to P. So in some sense, we work relative to a variant of the sphere spectrum, a spherical polynomial ring, where you adjoin like a polynomial or power series variable to the sphere, and then you compute a relative version of TC relative to that, and then you descend along the map from the sphere to the spherical polynomial ring. So that's what we actually do. And that's a strategy which I guess I outlined a couple years ago in a paper with Achim Krause, and also Leo Wang had sort of used to calculate something like TC of the p-adic numbers. So that's a well-known strategy. And in order to make this work, I mean, I guess first of all I have to sort of understand this relative TC. And here's a tool to understand this relative TC and make this whole strategy work. That's if we have a ring spectrum, which I call SA, which is a p-complete E-infinity ring, which is flat over the sphere. And I guess, I mean, I'm denoting it this funnily SA because I think of it as a sort of fluffy land deformation of the ring A. I have this ring A, pi naught, and then it's a deformation. It's a flat deformation of that ring over the sphere. That's the way I think about it. And if you are in such a situation, then it turns out that also there's a variant of the Segal conjecture. The Tate construction on that ring is equivalent to the ring itself. So I get that the Frobenius is an endomorphism. And the claim is in such a situation, the Frobenius induces on pi naught a self-map, and that's a Frobenius lift. So Frobenius lift meaning this is now a map of rings. If I go mod p, it's the Frobenius of an ordinary ring. And such a structure is actually called a delta ring structure. I mean, a delta ring structure is slightly more subtle, but here, because of my flatness assumption, I'm p-torsion free, so this is literally what a delta ring structure is. So the point is, for every flat E-infinity algebra over the p-complete sphere, pi naught is a delta ring. And now what you do is actually you want to calculate relative, I mean, the example we have in mind for SA is S bracket Z. And now what you can do is you can sort of try to calculate this TC relative to this SA. And it turns out that this can be given by an algebraic theory. So what I mean, this has been like done if in the case that A is A-inf of a perfectoid ring, this has been done by Butt, Morrow, Scholze, and we generalized their theory, or the symptomic or prismatic cohomology of like Butt and Scholze, to this setting where we just work relative to a delta ring and not relative to a prism. And then we define a new theory which extends that theory, and we prove that this TC working relative to this guy admits a filtration whose associated graded is given by that cohomology. So the point is we have a completely algebraic description of this associated graded. I mean, if you can't follow what I'm saying here, just like sort of the zoomed out version is we have an algebraic, a filtration and an algebraic description of the associated graded. So in other words, a spectral sequence from something we understand. And I guess, as I say, this has been like established by Butt, Morrow, Scholze. We prove this slight extension to where we work relative to these flat E-infinity rings. And I mean, there are some technical assumptions. R has to be a P quasi LCI ring. Okay, good. So that's the theorem. And besides, I mean, this is literally how we compute TC of Z mod P to the K. It turns out that the algebra can be done. We can calculate these algebraic cohomology theories entirely in this case, because these are like the natural analog of quasi-regular semi-perfectoids. So you can write down formulas. Everything is nicely functorial. That's why it's important to have this extension. And then you sort of calculate the descent thing. And that's the kind of method. And as I say, this is a super general method. You just need to find some like base from which you can descend, over which you can sort of control the algebra. And that's certainly not bound to rings of the form Z mod P to the K or ZP. I think this is like super applicable to many cases now. Okay, anyways, and here's a fun corollary with which I will end. That's what I call ultimate Bergstedt periodicity. Because remember, we had this version, Bergstedt periodicity was a calculation of THHFP. And here I claim as a generalization, if you are in the situation where you have this flat ring spectrum SA, and I want to look at R being a quotient of A by an ideal which has a certain condition, which is called a prism condition by Butt and Scholze. I'm not going to tell you what it is, but it's a condition on an ideal in a ring. Then the claim is that THH in this generality relative SA satisfies Bergstedt periodicity. So in other words, it's two periodic or almost two periodic. This I is going to be an invertible ideal, so it's basically generated by a non-zero divisor, and then this is a polynomial ring over the ring itself. And so, I mean, Achim and me had written an earlier paper where we had collected a lot of versions of Bergstedt periodicity, and this generalizes all of them. So that's why I call it ultimate Bergstedt periodicity. And for example, if SA is the p-complete sphere, then, I mean, pi naught is the p-adic. You let the ideal be generated by p, then the ring is FP. This is how this generalizes Bergstedt periodicity. But as I say, it's much more general, and this is my picture. I mean, we call such an object a spectral prism. This is my picture of a spectral prism. So somehow the horizontal axis is the fluffy direction, the upper top is an ordinary prism. And there's a lot of exciting questions about these spectral prisms. Okay, I want to end my talk on this note, and thank you all.